Welcome to Notes 3.4 Part 2. In this set of notes, we are going to be talking about gravity problems, and we are also going to be talking about the relationship between velocity and acceleration. Picking up where we left off in Part 1, we are going to do a quick review of the linear motion stuff that we wrote down at the end of our last set of notes. So here we have position. We call that S of t most of the time. Sometimes you'll see X of t in some problems. I'd rather call it P of t for position of time. That's perfectly fine. Just be aware of the standard notation that we typically use. It'd be S of t or X of t typically. So position measures the distance from your starting position. And then it could also be positive or negative. Positive if I am moving forward or to the right, up, away from my starting position. Negative if I'm moving to the left or below my starting position. Then we have velocity. There's two different types of velocities that we're going to be looking at here. There's average velocity, which is the change in position over the change in time. So we're looking at time intervals. And visually, that would be the slope of the secant line from your position function. Instantaneous velocity, that is wanting to know the velocity at a single point of time. So visually, if I'm just looking at a single point of time slope, that would be the slope of the tangent line. And the slope of the tangent line is the derivative. So the derivative of S of t would be how we find the instantaneous velocity. In a word problem, you know that you're looking for instantaneous velocity if you see one of two things. If you see the words rates of change and with respect to, you know that you're doing instantaneous, because that's basically the verbiage for how you do derivative. You could also be asked about a single point of time versus an interval of times. Next, 4 bullet points are just talking about the signs for your velocity. So if I have a positive velocity, my particle is moving forward. If I have a negative velocity, my particle is moving backward. If I have a velocity of 0, my particle is either not moving / staying still for a moment of time or for a time interval. Or if it's a momentary velocity of 0, like a single moment, single second, that would be that my particle is turning around. So from going away to going back to my starting position or vice versa. And then if I just want to know the speed, I don't want to know the direction of where I'm going. I just want to know my raw speed of the particle. That would just be the absolute value of your velocity. What I would like to go over now is motion that is under the influence of gravity. Not all particles are going to be using gravitational pull to model their position or model their velocity. Like, think about it. If I have a helicopter, it's just going in the air. It's not like it's staying up. It's not falling with gravity. If I'm walking or running, yeah, I'm getting pulled to this Earth's surface, but my speed has nothing to do with gravitational pull. I'm not falling to the ground. So motion under the influence of gravity is talking about items that are falling because they are getting pulled back to the Earth's surface or back to whatever body's surface, like any planet's surface. So for our position function, that would be S of t equals S sub 0, so our initial position, plus v sub 0 times time, so that's the initial velocity times time, minus 1/2 gt squared. So 1/2 gravitational pull times time squared. G is for any sort of gravitational pull. That's your gravitational constant. I'm going to give you the 2 different types of gravitational constants that we use for Earth, but they do vary from planet to planet with what their gravitational pull is. Also, depending on what style of distance we are looking at, so whether it's meters or feet, our number could change a little bit. Then for velocity, I want you to write down what you think the velocity function is, remembering the relationship between velocity and position. So remember, velocity is the derivative of position. S sub 0 is a constant. It's whatever my initial position is. So when I take the derivative of a constant, it goes away. The next term, v sub 0, is my initial velocity. So let's say my initial velocity is 5. Derivative of 5t would just be 5. So it's my initial velocity. Minus, take the derivative of that last term. Remember, it's with respect to time, so t is our variable. Multiplying by 2, we get 1 is the coefficient multiplied by g. Reduce that power by 1 and we just get t. So the velocity function under the influence of gravity is initial velocity minus gravitational pull times time. And then at the bottom, we're just going to remember what all of these things stand for. S sub 0 is our initial position. V sub 0 is our initial velocity. And then G is our gravitational constant. I would like you to write that on Earth. The gravitational constant would either be 9.8 meters per second squared or 32 feet per second squared. So just be aware that if our distance is being measured in meters, we'll use the 9.8. If our distance is being measured in feet, we have to use the 32. Let's move on to our first example. A stone is shot with a slingshot vertically upwards with an initial velocity of 50 meters per second with an initial height of 10 meters. Because that stone is subject to gravity, it's going up and then gravity is going to pull it right back down. We have to use Galileo's formulas. So I would like you to go ahead and write your position and velocity formulas. I'm going to write them generally down and then I'll fill the numbers in when I'm done. I would also say, so long as you memorize your position formula, you don't necessarily need to memorize your velocity. You can just take the derivative of your position formula. So initial position 10, initial velocity is 50. And then the gravitational constant, because we have meters, our gravitational constant is going to be 9.8 meters per second squared. If I do 9.8 times 1/2, it's going to get me 4.9. So I'm just automatically going to put the 4.9 into the position function, and then this would be my 9.8t. Part B, find the velocity at times t equals 2. You know your velocity function, just go ahead and plug in 2. Make sure that you label your answer appropriately. Plugging that into our handy dandy calculator, we get 30.4. And then our label for this velocity is meters per second. So what that tells me is that at 2 seconds, because I have a positive velocity, it is still going upwards. It is still moving towards its vertex before it comes back down. See, what is the stone's maximum height and when does it reach that height? So at a maximum height, let's just draw like a quick graph. Started at 10. I don't know the scaling for my x-axis, so I'll just leave that alone. It's going up, and then it'll come back down to the ground eventually. At my maximum height, I have a horizontal tangent line. And when we have a horizontal tangent line, the slope of it is 0. So the slope of my tangent line, or my derivative, equals 0. So to find the maximum height, we're looking at where my derivative equals 0, or remember the derivative of position is my velocity. So we're going to take our velocity function and find where that equals 0. Find that time, and then what I want you to do is figure out the stone's maximum height at that time. I will have my answers on the screen here. I'm going to continue writing, and then I want you to make sure that you're checking your answers as I write this. Time was measured in seconds. And then I want to know the actual maximum height at that time. So I'm going to just go ahead and plug in 5.101 into my position function. I'm kind of running out of space, so I'll just put the final answer. Label for my height is in meters. So last question for example 1, what would the initial velocity need to be in order for the maximum height to reach 160 meters? So at my maximum height, which we did in the last problem, we knew that our velocity would be 0. I'm going to write that down. That'll kind of be like our jump off point. And honestly, this is a type of question that would probably take you a little bit of time to think about before you actually get a plan together for it. In these kind of problems, you just kind of write down, what do I know? What do I need to know? And how might I possibly get there? So I'm going to write my velocity function, set that equal to 0. But instead of using the initial velocity, I'm going to use v sub 0 because I am trying to figure out a new one. And that was 9.8 t. So I'm going to go ahead and set my velocity equal to 0. And what this is going to do is it's going to allow me to solve for a general time and a general velocity. So I'm going to solve for time. And then what I can do is plug that general time into my position function because I know that I want that maximum position to be 160. So subtract v sub 0 to the other side, divide by 9.8. We get v sub 0 divided by 9.8 equals t. So the time that it takes me to get to my maximum height is a ratio of my initial velocity and the gravitational pull. I'm going to take that generic time that it takes me to get to my maximum height and actually put that into my maximum, or put that into my position function. So remember, our position function is s of t equals my initial position, which we actually know we're still keeping that initial position. It didn't say anything about changing it. It's 10. But this time, we don't know what we would want the initial velocity to be. So I'm going to leave that as a v sub 0 minus 4.9 t squared. I know that I want my time to be the ratio of the initial velocity and the gravitational pull, because that's generally how long it takes me to get to that maximum height. And I know that I want the maximum height to be 160. So using my time of velocity divided by initial velocity divided by 9.8 in my position of 160. I'm going to plug that information in. And solve for that initial velocity since that is now my only variable. I am going to use, again, movie magic. And my answer will appear in 3, 2, 1. Okay. So basically we are ending up with positive or negative 54.22 as the initial velocity. Because we know that the slingshot is going up, or the item is going up from the slingshot before it comes down, we're going to be using the initial velocity of positive 54.22. And the label would be meters per second. If you have any questions, make sure you write that down. Moving on to the next goal that we have for the set of notes, talking about the relationship between velocity and acceleration. I'm going to read the little paragraph and then we're going to get into an example. So acceleration is a vector quantity that is defined as the rate at which an object changes its velocity. So it's the change in velocity over time. So basically at this point, it goes from position to velocity to acceleration. Velocity is the derivative of position. Acceleration is the derivative of velocity, which it means it's the second derivative of position. An object is accelerating if it's changing its velocity, whether that's positive acceleration, negative acceleration. We just say it's accelerating if it's changing its velocity. If an object is not changing its velocity, then the object is not accelerating. So in example 2, it says for each velocity acceleration table, circle whether the object is moving forward or backward and whether it is speeding up or slowing down. I want you to do this by just looking at the velocity columns. We're going to make an observation with acceleration afterwards. And remember, we determine if the object is moving forward or moving backward by if the velocity is positive or negative. And then speeding up or slowing down, just look at the relationship of those velocities. Is it getting further away from 0 or is it getting closer to a velocity of 0? So pause the video and I would like you to try all 4 of these. In this first table here, our velocities are all positive, so we're moving forward. And then the velocities are getting bigger and bigger and bigger, so it looks like we are speeding up. In the second table, the velocities are all negative, so we are moving backwards. And then all the velocities are getting closer and closer to 0, so we are slowing down. Okay, next table. Velocities are all positive, so we are moving forward. And then the velocities are getting closer to 0. So we are slowing down. Last table, velocities are negative, so we're moving backwards. And then our velocities are getting bigger and bigger and bigger, just in the negative direction. So we would say that it is speeding up. What I would like you to do is look at all of the velocity and acceleration relationships that we have here and see what you are noticing. So for all of the velocities that are the same sign, what are the particles doing? For all of the velocity acceleration tables where they are the opposite signs from one another, what is the particle doing? If you notice in the two tables, this one and this one, where the velocities and accelerations have the same time, our particle is speeding up. It's just happened to be in that one direction that the particle is moving. In the tables where we have opposite signs for the velocity and the acceleration, our particle is slowing down. That's not a coincidence, so we're going to write that in this table. Because when an object is speeding up, velocity and acceleration will have the same sign. When an object is slowing down, velocity and acceleration will have the opposite signs. So in the last example, it says a particle moves along the x-axis so that at time 0 to 12, its velocity is given by that function. Determine all of the intervals where the particle is speeding up. So we need to basically figure out where the velocity is positive versus negative and where the acceleration is positive versus negative. That way we can see which intervals they have the exact same signs. This is not subject to gravity, so we are just using the velocity function that we're given. And keep in mind, the boundary between positive and negative is 0. So we're basically going to find where velocity is 0 and find where our acceleration is 0. Remember, acceleration is the derivative of velocity. So go ahead and find that derivative. You should get negative 6t, because when you multiply by the 2, you get negative 6. Subtract the power by 1, you get a 1. Derivative of 4t is just 4. Derivative of 15 is 0. So like I said, we'll do the same thing by finding the boundary between where the acceleration is positive versus negative. Using movie magic, I'm going to have the answers appear in 3, 2, 1. Now, because the negative 5/3 is out of our time range, that is not going to be one of the times that we use. It's kind of like an extraneous time. So it looks like velocity is 0 at time 3 and acceleration is 0 at 2/3. I'm going to put both of those times on the same number line here. Keeping in mind that we're going from 0 to 12. 2/3 is going to go first. 3 is next. I'm not looking at like actually scaling this appropriately. And in each interval, I want to check out my velocity signs and my acceleration signs. So I'm going to put my velocity signs up top. And I'll put my acceleration times or signs in the bottom. So let's see, something that's smaller than 2/3 would be half. So if I plug half into my velocity function, it'd be negative 3 times half squared plus 4 times half plus 15. Let's get that put into our calculator. And we're getting something that's positive. I don't care what the number is per se, but I just want to know that it's positive. If I plug half into my acceleration function, -6 times half plus 4. That is also positive. So that tells me that this interval right here is speeding up because my acceleration and my velocity are the same sign. I want you to do the next 2 sections, and I will have my signs appear in 3, 2, 1. I'm also, so in the next section from 2/3 to 3 seconds, the signs are the opposite. So those are that in that section, my particle would be slowing down. In the last interval from 3 to 12 seconds, I have the same signs again. So my particle would be speeding up. Because they are both negative though, that tells me that although it's speeding up, it's moving in the backwards direction. So that's okay. All right, in the end, my particle is speeding up from 0 seconds to 2/3 seconds and 3 seconds to 12 seconds. I'm not including the endpoints because technically my particle is transitioning from speeding up to slowing down and vice versa. Or my particle is just getting started moving or just ending moving. And that is it. If you have any questions, make sure you ask.